Normal approximation for the sample proportion. So here we're going to look at inferential statistics, which we can use if we get a sample of statistics from an entire population and use them to infer information about the entire population. And there's something called the central limit theorem, which basically states that the more data we get, that it will approach the normal distribution, which obviously we know is in the shape of a bell curve. And the more data that we can collect, the closer we can get to this approximation. Now, there's a couple of things we need to be able to calculate here for sample proportion to get approximations to a normal distribution. And the first thing we want to talk about is a sample proportion. Now, a sample proportion is denoted by p hat. So this is our sample proportion. And this equals our observation over our sample size. So this is our observation, or like number of observations, over our sample size. And it's probably worth noting that this is a sample proportion. So we're taking it from data from an entire population. So we can have something called the population proportion, which is capital P hat. And this would be the ideal case where we'd have the number of observations over n, but in this case, n was the entire population size. And the sample proportion can be a reasonable estimate to the sample population if it meets some certain conditions. And those conditions are that n times the sample proportion has to be greater than or equal to 5, and n, so our sample size, multiplied by 1 minus our sample proportion has to also be greater than or equal to 5. So we have to pass both of these conditions for this to be a good enough approximation. And if they are, we get a couple more results saying the expected value of our population proportion will approximately equal the sample proportion. We also get the standard deviation of our population proportion will approximately equal the square root of our sample proportion times 1 minus the sample proportion over our sample size. So this is our expected value and this is our standard deviation, which is also called our standard error. And let's go ahead and use these to look at some examples. So let's have a look. If we have a school that consists of 1,125 students and 247 responded to a survey, asking if they enjoyed maths, and 144 said they enjoyed maths. The first thing we want to do is we want to just note down what's the sample size. So if 247 responded to the survey, that means that's our sample size. So that's just 247. Next, we want to know what the observation value is. So the number of observations. Well, this is just the number of people that enjoyed maths, 144. Next, we're after the sample proportion. So we're after p hat. And we just get p hat by doing our observations over our sample size. So we get 144 over 247. We can just leave it like that. We could write as a decimal. It's about 0.583. Now we're after the population proportion, so capital P hat. Now, it's kind of a trick question because we can't actually know that. The only way we could know that is if all 1,125 students responded to the survey. That's the only way to find the population proportion. So this is actually unknown. Next, we're after the expected value of the population proportion. And we know that approximately equals the value of p hat, our sample proportion, and that's just going to equal 0.583. Now let's find our standard error, which we know is going to approximately equal the square root of p hat times 1 minus p hat all over n. So we're going to get the square root of 0.583 times 1 minus 0.583 all over 247, which is going to be 0.031 to 3 decimal places. Now the last thing we want to do is we want to know, can this distribution be approximated by a normal distribution? And we know if that's the case, it has to satisfy both of these conditions here. So we're going to get n, which is 247, times our sample proportion, which is 144 over 247, and it has to be greater than or equal to 5. So the 247s will cancel, and we get 144 is greater than or equal to 5, which is true. So it satisfies that one. Now we need to check the other one. So we get 247 times 1 minus 0.583. And that has to be greater than or equal to 5. And we end up getting 103 is greater than or equal to 5, which is also true. And therefore, this distribution can be approximated using a normal distribution.